Welcome to the day 3 of the chapter S block elements. This is chapter 10, and in the previous class, I was talking about group 1 compounds like sodium hydroxide, sodium chloride, their uses, the principle of preparation by the Kastner-Kellner cell. Okay, today I'm going to proceed further in this chapter and discuss quickly with you with regard to sodium carbonate. Have a look over here, sodium carbonate, article 10.3.2, which is also called soda ash or washing soda, Na2CO3. Now, the principle and equation of Solvay process. Over here, only the Solvay process is there in the syllabus. Okay. So here for the Solvay process, if you look at the next page, you will find over there. Just a second. Solvay process, the diagram is there. Solvay process for the manufacture of sodium carbonate. This is the diagram, which is not required actually, but principle and equation is only required. So if you look at the details of the process over here, the principle is there. On commercial scale, sodium carbonate is prepared by Solvay process, which is also given a name as ammonia soda process. Principle is like this. When a concentrated solution of brine, that is sodium chloride, is saturated with ammonia, okay, and then with carbon dioxide, sodium hydrogen carbonate is formed as shown below. So this is the principle. Now this sodium hydrogen carbonate thus formed is sparingly soluble in the presence of excess of carbon dioxide and is removed by filtration. It is ignited to get sodium carbonate. So the principle over here is when ammonia gas, carbon dioxide, it is mixed with water, it is forming ammonium carbonate, which when reacted with sodium carbonate further, it is giving a bicarbonate. Now this bicarbonate, upon heating, it is producing the sodium carbonate salt. Now only the equations required. Please do not go for the extra details of the reaction. The details of the process, it is not necessary. Okay. Now only the principle and the equations. Equations are here. This is required. After that, moving to the next page, page 606. Over here, the details are not required. Then coming to the properties now. Properties over here. Properties of sodium carbonate. Now, properties you can see. If you look at sodium carbonate, it is a white crystalline solid and forms decahydrate. It is commonly known as washing soda. So this is one property which you should try to remember. Okay, the color is white crystalline solid. It is, however, readily soluble in water, and its solution is alkaline due to what? Hydrolysis. It is an efflorescent substance and loses its water of crystallization to form a monohydrate over here like this. Action of heat. If you heat sodium carbonate decahydrate to 373 Kelvin, that is 100 degrees Celsius, it forms a monohydrate. Further heating, it makes it anhydrous. Action of acids. If you react this sodium carbonate with acids like hydrochloric acid or carbon dioxide gas is formed over here. In the case you use sodium bicarbonate, otherwise you will get sodium bicarbonate and sodium chloride only. Action of carbon dioxide. If you react with carbon dioxide and water, the sodium carbonate becomes a bicarbonate. Okay, so here the uses are more important. Uses of sodium carbonate is more important. It is used in the manufacture of glass, borax powder, soap, caustic soda, etc. It is used for washing purposes in laundry. It is used for softening of hard water. It is used as a mixture of sodium carbonate and potassium carbonate. It is used in as a fusion mixture. It is used in paper, textile, and paint industries. It is used as a reagent in the chemistry lab. Okay, so these are the things under sodium, carbonate. Now the next thing which is required is sodium bicarbonate, preparation from sodium carbonate and uses only. Okay, so sodium bicarbonate is the next thing we are going to study, which is also commonly called NaHCO3 baking soda. Now only the preparation is required. Remember that only the preparation is required. Okay. Now just a second. Just go through this. I'll just join you in a while over here. Can you hear me?
Yes, sir.
Can you hear me voice? Hello, can you hear me?
Yes, sir.
Okay. Anyway, there's some problem with the microphone. Okay, never mind. Now the sodium carbonate, which is called baking soda, it's preparation of sodium carbonate. This one bicarbonate from sodium carbonate is only required. Okay, so for this, it is an intermediate product which is already given over here. How to prepare sodium bicarbonate? By passing carbon dioxide gas through its concentrated aqueous solution. So if you take a concentrated aqueous solution of sodium carbonate and pass carbon dioxide gas, then you get what you call sodium bicarbonate. Okay, only that much is required, and uses are required. Uses, it's given over here. Preparation is already given over here. Properties, you may not go through it. Leave out the properties. Okay, leave out the properties, but uses are required. Now, this sodium bicarbonate is used as a component of baking powder. The baking powder which you go and buy from the grocery shops, that is sodium bicarbonate. It is used as medicine in medicine as a mild antiseptic for skin infection. So if your skin is burning and all, if it is there is skin irritation, and you can take some baking soda and put it over there. That will also it will relieve from the pain because it is an antiseptic. It is used in the fire extinguishers. It is used for making effervescent drinks. It is used as a reagent in the lab. Okay, so these were the preparation and uses of sodium bicarbonate. Now, sodium carbonate I've already discussed in the previous class. Moving further in this chapter to the next compound, that is called sodium thiosulfate. That is article 10.3.5. It is on page number 609. Article 10.3.5. Now, sodium thiosulfate preparation from sodium sulfite. Only this one. Only this one is required. Others are not required. Okay. So, from sodium sulfite, you can prepare what you call sodium thiosulfate by reacting with sulfur powder S8. Okay, at 373 Kelvin, that is 100 degrees Celsius, to form sodium thiosulfate. Okay, so only this method, only this chemical reaction is required. Okay, after that, after the preparation from sodium sulfite, its reaction with first one under properties, some reactions are necessary over here. Now the reactions which are necessary, I tell you, which is required. It's reaction with iodine and dilute acids and silver nitrate. So the reaction with iodine is over here. So iodine oxidizes to into sodium tetrathionate. So this reaction is required. Very, very important reaction. So the reaction of sodium thiosulfate with iodine is very, very important. Okay, this you learn. Na2H2O3 plus I2 is giving sodium iodide plus sodium tetrathionate. It is getting oxidized to sodium tetrathionate, Na2S4O6. Okay. After that, reaction with dilute acids, that is number 6. So if you take dilute acids, hydrochloric acid and dilute sulfuric acid, and react with sodium thiosulfate, you're getting sulfur particles, sulfur powder over there. So remember, this one is also important. Okay, that this reaction is also important over here. And now this reaction, this first reaction was there in class 10 syllabus also. Okay, class 10 textbook. It is not in the syllabus, but it is there in the class 10 textbook also, where when you react sodium thiosulfate, a colorless solution with hydrochloric acid, the solution turns turbid due to the formation of sulfur particles. Similarly, if you react with sulfuric acid dilute, again the solution will turn turbid due to the formation of sulfur particles, and the other products are salt, sulfur dioxide gas, and water. Okay, so this reaction is required. After that, the next reaction which is required, which is important for you all, is reaction of sodium thiosulfate with silver nitrate solution. Silver nitrate solution. Now here, when a dilute solution of sodium thiosulfate is treated with silver nitrate, a white precipitate is first obtained. This is the white precipitate, silver Ag2S2O3, which quickly changes to yellow, brown, and finally black due to the formation of silver sulfide. So what happens? An unstable compound is formed. Okay, that is called silver thiosulfate. You can call it silver thiosulfate, which is unstable. So what happens? This compound immediately converts itself into what you call over here. Not this one. Just a second. This one, it converts itself immediately in the presence of water to form a black colored, final black colored substance. But the process is so beautiful that first the color changes to yellow, then it becomes brown, and then finally it becomes black. And this black color is due to the formation of silver sulfide. So this reaction is important with regard to its observation. Okay, now after this, the uses of sodium thiosulfate. The uses of sodium thiosulfate that is required. Okay, now the uses are, it is used as a fixer in photography. Suppose if you want to print out something, print out a photograph, so it gets printed out, the photograph gets printed on the photo paper, so it has to be fixed over there, otherwise the photo will come out again. That's why if you use sodium thiosulfate in the solution in which you dip the photographic paper and take it out and dry it, then that is acting as a fixer in photography. It is used as an anti-chlor in bleaching industry to remove the excess of chlorine from textile in fiber. That means if you are using what do you call chlorine to bleach clothes in the textile industry, the clothes will smell of chlorine. So if you want to remove the smell of chlorine, then you can use sodium thiosulfate, which is called anti-chlor, which is called an anti-chlor, which removes the smell of chlorine from the clothes. After that, it is used as a reagent in the lab for iodometric titration. In the chemistry lab, we use it for iodometric titration, which you will be doing in class 12. Okay. Now it is used also in the extraction of silver and gold and silver. Okay. Now these were the compounds of group 1 elements. Okay. Now before going to the compounds of group 2 elements, there are some important things over here to understand. That is called biological importance of sodium and potassium in the biological system. Now we know sodium and potassium, they play a vital role in biological systems. A brief explanation is given over here. Sodium is a vital element present in our body. A typical 70 kilo man contains 90 gram of sodium. Just imagine. If you are weighing 70 kg, you should contain, your body should have 90 gram of sodium. Otherwise, you will be facing some deficiency diseases. Sodium ions are found primarily on the outside of cells, which are located in blood plasma and in the interstitial fluid surrounding the cells. Now, these sodium ions play a very important role in the body. They regulate the flow of water. So that is the function. So, importance of sodium is, sodium ions, they regulate, they control the flow of water in the cell membranes and in transport of sugars and amino acids into cells. So, if you are having less sodium in your body, that means your body will have less sugar, means there will be again a disease. If there is more sugar which is not controlled by the sodium, then what will happen? You will you get affected by the, because of the disease of the pancreas, and that will lead to diabetic conditions in your system. Okay, so now after that, moving further to the biological importance of potassium over here. A normal 70 kg man contains more. You should contain 170 gram of potassium. Potassium ions are the most abundant cations within cell fluids. In cell fluids, they activate many enzymes and participate in the oxidation of glucose to produce ATP, adenosine triphosphate. Okay, it is an enzyme. Then ATP acts as a source of energy for the energy required by the body in different activities. Potassium ions, along with sodium ions, also participate in the transmission of nerve signals from the brain to the different parts of the human body. Now, whereas sodium is present to an extent of 143 millimoles per liter in blood plasma, the concentration of potassium in blood, it is only about 5 millimoles per liter within the red blood cells. This concentration may change to 10 millimoles per liter for sodium and 105 millimoles per liter for potassium. And these ionic gradients are due to the discriminatory mechanism called sodium potassium pump, which operates across the cell membrane. So there is a pump, the cell membrane, because of osmosis, okay, because of diffusion, they allow liquids to pass in, enter the cell, and leave out of the cell. So potassium and sodium, they have a very important role in the human system, biological system. Okay, now after that we move to the group 2 elements, their detailed study, which are called alkaline earth metals. Group 2 elements, which are called alkaline earth metals, and the group 2 elements are, we know it is beryllium, magnesium, calcium, strontium, barium, radium. Okay, the last element, radium, is radioactive in nature. These elements are collectively called alkaline earth metals. Why? Because if you react them with water, they will form what we call, they'll form basic solutions. Okay, they'll form basic solutions. That's why they are called normally alkaline earth metals. Now, the name alkaline earth metals was initially given to calcium, strontium, and barium because the oxide of the elements were alkaline and exist in the earth. Nowadays, the term alkaline earth metal is used to represent all the elements of this group particularly. Now, with regard to the occurrence of the alkaline earth metals, over here on page number 610, alkaline earth metals are also quite reactive and do not occur in the free state. So that's natural. They are widely used, distributed in nature in the combined state. As you remember, they are in the combined form in the form of carbonates, sulfates, silicates, and phosphates. Now, the first member of the group, that is beryllium, it is the 51st most abundant element in the Earth's crust. 51st. It is mainly found as beryl, BeO.Al2O3.6SiO2, or chrysoberyl, BeO.Al2O3, or panacite, Be2SiO4, etc. Now, magnesium, the next element in this group, it is the sixth most abundant element in the Earth's crust and occurs as magnesite, MgCO3. This you try to remember for magnesium. Dolomite, magnesium carbonate, calcium carbonate; epsomite, magnesium sulfate, heptahydrate; carnallite, potassium chloride, MgCl2.6H2O. It also occurs to an extent of 0.13%, where in seawater, in the form of chlorides. You will find magnesium in the form of chlorides and sulfates in seawater. The next element, it is calcium, is the fifth. Magnesium and calcium almost similar. This one is the fifth most abundant element in the crust of the earth. Now it is important. Its important minerals in which it is found is gypsum, that is calcium sulfate dihydrate or anhydrite. Okay, calcium sulfate; fluorspar, that is calcium chloride; phosphorite, that is calcium phosphate; limestone, that is calcium carbonate. Now coming to the next two elements, strontium and barium, these are less abundant, much less abundant in nature. The important minerals of strontium, it's called strontionite, SrCO3, strontium carbonate chemically, and celestine. I would request you to learn this formula, strontium carbonate. Okay, because I will not tell you the reason why, but when you go to class 12, while doing a practical chemistry, class 12 practical chemistry, you will come across this compound in the group analysis. Okay, and celestine, strontium sulfate, while those of barium are barytes, barium sulfate, and witherite, that is barium carbonate. The last member of the group, radium, is radioactive in nature and is extremely rare. It has to be extracted. It is radioactive in nature. So it is quite dangerous to handle radioactive elements of the air. Now, coming to the General characteristics of the alkaline earth metals. They are discussed one by one, point by point. The first one, it's electronic configuration. Now, we know alkaline earth metals belong to the S block. That means the differentiating electron will enter the S subshell of the valence shell and have electronic configuration of the type NS2, where N represents the outermost or the principal quantum number of the valence shell. Now, some electronic configurations of the what we call these group 2 elements are given over here. Okay, you can have a look and practice them. Practice writing the electronic configuration provided the atomic number is given to you all. Okay, so practice writing the electronic configuration. Then we come to the physical properties of alkaline earth metals. Okay, over here physical properties. This chart is just a comparative what do you call visible chart which you can go through it just to compare their boiling points or the density or the electronegativity or the hydration energy or the abundance in the earth crust. But more importantly, we'll discuss the properties over here. Physical state number one on page 612. The alkaline earth metals are grayish white, malleable, and they are ductile, and they possess a metallic luster. Of course, they are metals. They are harder than alkali metals. The hardness decreases on moving down the group. Remember this. Then after that, yes, then atomic and ionic radii. The atomic and ionic radii of alkaline metals are fairly large, but smaller than those of the corresponding alkali metals. Okay. The atomic and ionic radii increase in going from beryllium to radium. If you move from top to bottom, the radii, atomic and ionic, it is increasing. Explanation I will not tell why it is increasing, because if you move from top to bottom, the principal quantum number is increasing, the number of shells are increasing. That's how the atomic as well as the ionic radii is going to increase. Now, after that, coming to density. The densities of alkaline metals are much higher than those of alkali metals. Moreover, the density of these elements do not vary regularly on going down the group. The densities first is decrease in going from beryllium to calcium and then increase sharply from calcium to radium. This is a small anomaly over here. Densities, the trend is not uniform. Okay. Explanation not so important. Coming down to melting and boiling points, which is important. The melting and boiling points of the alkaline earth metals here, the alkaline earth metals, they have much higher melting and boiling points as compared to those of alkali metals. Okay, if you compare to those of alkali metals, their melting and boiling points are higher. No regular trend in the melting and boiling point is observed on moving down the group. Okay, they may vary slightly or they may vary highly. Okay, now due to smaller size, the atoms or ions of alkaline metals are packed more closely. So that's the main reason. Moreover, the alkaline metals have two valence electrons, whereas alkali metals have only one. The large number of valence electrons leads to the formation of stronger metallic bonds. Okay, that's why the melting points are and the boiling points are higher, because higher the number of valence electrons, more is the tendency of those elements to form stronger bonds which are metallic. Okay, then number five, the ionization enthalpy or ionization energy. The ionization enthalpy of alkaline earth metals show the following trend. Number A, the ionization energy of alkaline metals are quite low. That's why they are metallic. However, they are higher than those of the corresponding alkali metals. So, reasoning you go through this on your own. It is not so difficult. Then moving to the next column over here. Number B, the ionization energies of alkaline earth metals decrease on moving down the group. If you are moving from top to bottom, we need less energy to remove the electrons from the valence shell, because the size becomes bigger, the size of the atom or the ion becomes bigger. Okay, then coming further down over here, the explanation is given why the second ionization energy is much higher compared to the first. So it is given over here. Next one, number 6, is electronegativity. Alkaline earth metals have low values of electronegativity because they are metallic in nature. They are electropositive. The electronegativity decreases in going down the group. Alkaline earth metals are more electronegative than alkali metals. So, if you're moving from left to right across the period, the electronegativity values across the period, it is increasing. But if you compare alkaline earth metals with the alkali metals, the alkaline earth metals, they have higher. You can say they have higher compared to alkali metals, but comparatively, if you compare with the 17 or group 18 elements, the alkaline earth metals, they will have low values of electronegativity. Okay. Then moving further to page 613 now, the electropositive character, which is metallic nature. The alkaline earth metals are highly electropositive and therefore possess high metallic character. However, they are less electropositive than alkali metals. The electropositive character or metallic character of the metals increases in going down the group because the size is becoming bigger, and in the valence shell the number of electrons is more as compared to the alkali metals. Okay. Now, number 8, number 8 over here, tendency to form dipositive ions. Alkaline earth metals in their valence shell, they have two electrons, and these two electrons can be easily given away to form dipositive ions. Okay, that's why they have a good tendency to form dipositive ions. Okay, now after that, coming to the solid state. Now, in the solid state, the dipositive cations form stronger lattice as compared to those formed by monopositive ions. That's why, that is how, because of the high lattice energy, their what you call melting and boiling points tend to be higher. Okay. Then moving to the second column over here, nature of dipositive. What is the nature? The dipositive ions of alkaline earth metals are formed by the loss of two electrons, okay, from the parent atoms. So you can see over here, illustration is given. All the electrons present in them are paired. Due to the presence of all the electrons paired, the dipositive ions of alkaline earth metals are colorless and they are dimagnetic. So please underline this. Nature. Under nature, all the electrons present in them are paired, inner electrons. Due to the presence of all the electrons paired, the dipositive ions of alkaline earth metals are colorless and they are diamagnetic. They are not repelled in magnetic fields. Okay. Now, looking at the flame coloration, the properties of these alkaline earth metals, calcium on the non-luminous flame, it will show brick red color. Barium will show apple green color. Strontium is crimson, and radium, radioactive, will also show crimson. Okay. So explanation is similar to what I have explained for the alkali metals, flame coloration. The electrons, these metals upon heating, the electrons get excited to the high energy orbitals. So and those high energy orbital states are short lived, so those electrons have to jump down again to the lower energy states, and during that jumping down of the electrons from the high energy orbitals or the energy states to the low energy orbitals, there is dissipation, release of energy, which corresponds to a particular color in the visible spectrum. Okay. Now after that, moving to page 614, coming to the chemical properties of alkaline earth metals. Chemical properties of alkaline earth metals. Okay. Have a look. The chemical properties of alkaline earth metals. Look at the first paragraph carefully. Look at the first paragraph very carefully. Okay. Now here in the first paragraph it is written, the alkaline earth metals are very reactive elements. This is an important, very important point over here. The alkaline earth metals are very reactive elements. What are they? They are very reactive elements. You must know that. Now, since they are very reactive elements, the reactivity is but less than that of alkali metals. This is one important sentence I'll tell you several times. The alkaline earth metals are very reactive elements, although the reactivity is less than that of alkali metals. Reactivity is less because they have two electrons. And if you are moving from left to right across the period, or moving from alkali metals to alkaline earth metals, you will find that the size of the atom becomes smaller because the number of shells is not increasing. The number of shells is same across the period. So here the high reactivity of these elements compared to the other elements correspondingly will be attributed to their low ionization energy. The reactivity of alkaline earth metals increases on moving down the group. That is quite peculiar. Now, some important chemical properties have been discussed over here. Like number one, if you look at action of air, Due to high reactivity, these elements are oxidized by atmospheric air and they get tarnished. Okay. Beryllium and magnesium, being less reactive, are not much affected in air. However, if you talk about calcium and strontium, are easily tarnished in air, while barium burns almost instantaneously when exposed to atmospheric air. So this sentence becomes important over here. Barium. This barium burns almost instantly when exposed to air. Okay, just have a look. Just have a look at the first one, action of air. Okay, first one, that is action of air. In this action of air, what is important? I have told you, calcium and strontium are easily tarnished in air, while barium burns almost immediately, spontaneously when exposed to atmosphere. So you can understand how dangerous it is to expose barium. Okay, then now now coming to the next one, the next chemical property, reaction with, if I talk about reaction over here with oxygen. So these elements of group 2, they react with oxygen to form the respective metal oxide. They can form monoxides, which can further react with oxygen to form peroxide also. Okay. Now what are the characteristics of oxides? The oxides of this group 2 alkaline elements are basic in nature, basic character. Have a look. Beryllium oxide is amphoteric in nature. Others are basic. Like if you talk about magnesium oxide, calcium oxide, basic. Whether it is weakly or highly, but it is basic. Okay. The basic character of the oxides of alkaline earth metals increases on moving down the group. Now solubility in water. Beryllium oxide and magnesium oxide are insoluble in water, while the other oxides, slake in water to give hydroxide. They react with water. See, look over here. Hydroxide are being formed. Okay. So that is what you have to remember over here. Stability. The oxides of these metals are very stable due to the high lattice energies. Crystal structure. Beryllium oxide possesses covalent lattice with coordination number 4. It is predominantly covalent and it is extremely hard solid. It is so hard that it can scratch even quartz. It is very hard, beryllium oxide. The oxides of other metals possess sodium chloride type lattice and coordination number 6. Coordination number 6 means what? There are 6 atoms surrounding the central atom in the crystal lattice. Okay. Now look at number 3. That is reaction with water. Formation of hydroxides. So when these metals react with water, they generally form hydroxides, whether it is beryllium or magnesium or calcium or strontium. But that is not so important over here. What is important is the characteristics of the hydroxides. The basic character of hydroxides, remember over here, this order is important. Except beryllium hydroxides, the hydroxides of all other alkaline earth metals are basic in nature and their basic strength increases on moving down the group. So if you're moving from top to bottom, beryllium hydroxide towards barium hydroxide, you will find that barium hydroxide is highly basic in nature. The explanation is given over here. The basic strength of a hydroxide depends upon what? Upon the extent to which it dissociates in solution to give hydroxyl ions. So, if it is capable of dissociating a large number of hydroxyl ions in solution, that means it is more basic in nature. So, you can imagine magnesium hydroxide will not dissociate, it will dissociate to a very low extent in aqueous solution to produce hydroxyl ions. Okay, so the explanation is given over here for that. Solubility in water, again you learn this order. The fairly soluble one is barium hydroxide, and the most soluble, almost insoluble one over here is beryllium hydroxide. Okay, magnesium and calcium hydroxide are sparingly soluble. Strontium hydroxide is more soluble. Okay, so solubility in water increases this way. Okay, this trend you must remember. Number 4, reaction with acids. Reaction with acids. Alkaline earth metals react with dilute acids to form corresponding salts with the liberation of hydrogen gas. So, the two reactive alkaline earth metals, magnesium and calcium, react with acids, dilute hydrochloric acid to give hydrogen gas. Number 5, reaction with alkalis, except beryllium. No other alkaline earth metals react with any other alkali. So, number 5 becomes important over here. Okay. only beryllium. Then reaction with hydrogen. So this beryllium chloride, talk about the elements over here, whether it is magnesium, calcium, strontium, barium, react with hydrogen to form alkaline earth metal hydride. Okay, hydrides are formed. Now, over here, beryllium hydride can be obtained also by the reduction of beryllium chloride with lithium aluminum hydride. That is a reducing agent. Okay. The characteristics, will not go through the characteristics. Okay. Then we'll talk about the halides number 7 over here. Number 7 is halides. Over here, halides of these metals can also be obtained by action of halogen acids on metals, their oxides, hydroxides, and carbonates. So here you can obtain the halides reacting with halogen acids over here. Okay, MX2 or this way. Okay. Now reaction 1 equation is given over here. Beryllium chloride is usually prepared from its oxide by this equation. React beryllium oxide, monoxide with carbon and chlorine prepare beryllium chloride and liberate a poisonous gas, that is carbon monoxide. Characteristics, it is not mentioned over there in the what you call syllabus, so we'll just skip it. Now look at the structure of beryllium chloride in the solid state. Okay, carbonates. Under carbonates, just remember the characteristics of carbonates: solubility in water, thermal stability. It is quite stable. Calcium carbonate is quite stable to heat. Okay, so this part you remember. Try to remember this order. Barium carbonate is very stable. That's why it is reading a very high temperature, almost around 1633 Kelvin temperature. Okay. Sulfates. Alkaline earth metals form sulfates of the type MsO4. So they are forming sulfates. Now, with regard to sulfates, also remember the characteristics of sulfates. This solubility in water only, nothing more than that. Okay. Oxalates, you can leave it out. Nitrates, you can go through the nitrates. The stability of the nitrates of these compounds like magnesium nitrate, calcium nitrate, strontium and barium nitrate over here. Strontium and barium nitrates are used in pyrotechnics for giving red and green colored flames. Reducing nature, this is important. Alkaline earth metals show reducing character, but they are weaker reducing agents than the alkali metals. That much only. Complex compounds. Alkaline earth metals have tendency to form complex compounds. This complex, this tendency decreases on moving down the group. So they will form complex compounds. Okay. Then after that, we come to the most important part of this part of the chapter, that is called distinctive or anomalous behavior of beryllium, which is the first element of this group. Now, beryllium is the smallest of all the other alkaline earth metals. That's why it is distinct, it is anomalous in character. It has highest ionization energy. The electronegativity of beryllium is comparatively higher than that of the other elements. Okay. It does not possess any d orbital. That is why it behaves differently from the other elements of this group. So these are the three important things you must remember from this anomalous behavior of beryllium. Okay. So the properties are given point wise. Go through these properties yourself. It is hardest of all alkaline metals, higher melting point. Beryllium compounds are predominantly covalent. It does not decompose even water at high temperatures. It doesn't react with acids to liberate hydrogen. Okay. But oxides of beryllium is reacting with hydrochloric acid and alkali to form salt and water. Okay. So that is there. Now resemblance between beryllium, this part of the chapter, with beryllium and aluminum, which is called diagonal relationship, I will do in the next class tomorrow morning. That is tomorrow I have a class with you in the first period. Okay, so with this, I would like to end my class over here only. Okay, but just hang on because I need to record your attendance. So today is 27th of October 2021. So till here, tomorrow I'll start from this. This is article 10.5.4. Okay, so but hang on, I need to record your attendance digitally. Your attendance is being downloaded. Okay, it is downloaded already. Thank you so much. Have a nice day.